So I mentioned that the temperature was specified in one of those problems because the rate constant depends on the temperature. Most chemical reactions are very sensitive to changes in temperature. The rate is very sensitive to changes in temperature. As an example, a 10 degrees Celsius increase in temperature can double or even triple the rate of typical biochemical reactions. And that's why your body regulates your temperature so tightly, because it needs those reactions to be happening at a predictable rate, not too fast, not too slow. So the rate constant is only a constant at the same temperature. You change the temperature, rate constant changes. So the reaction rate temperature dependence is inside of the temperature dependence of the rate constant. Rate constants generally increase with temperature, but not always. So let me introduce you to the Arrhenius equation. This gives us the relationship between the rate constant and the temperature. Just like with gas laws, we measure the temperature here in Kelvin. The reason being is that we can't have any zero temperatures. And by using the Kelvin scale, we never have zero. So the rate constant is equal to A, the frequency factor, times E raised to the negative EA over RT. EA is the activation energy. R is the ideal gas constant. Here we're going to use the 8.314 joules per mole Kelvin version. Activation energy would be measured in joules. And T is the temperature in kelvins. So this is the inverse natural log of negative EA over RT. So what is this frequency factor? What is activation energy? So here we have an energy diagram for this reaction between hydrogen and oxygen to form water. Here's the energy of the reactants, the energy of the products. The products are lower in energy than the reactants. So this reaction is energetically favorable. Everything in nature tends to go towards lower energy, right? So we would expect this reaction to proceed. But there's a barrier in the middle. So even though it's energetically favorable, there is still some energy required for it to occur. And that's represented here by this activation energy. It's an energy barrier that must be overcome. The frequency factor is related to how many times do the reactants approach this barrier, and how many times are they successful then? So we approach the barrier, sometimes we're successful, sometimes we're not. But the more frequently the barrier is approached, the more times you'll get over it. Right? If you never approach the barrier, you'll never get over it. So it's the number of times the reactants approach per unit of time. So let's look at a simple reaction here. We have one reactant and one product. This is methyl isonitrile, and this is acetonitrile. You don't need to know those names. The difference here is this one has the nitrogen in the middle, and this one has the carbon in the middle. This molecule can rearrange into this molecule. Well, that seems a little weird, doesn't it? It is a little weird. It requires some energy. You could think of this as being like this little thing on the end. You kind of have to pull it out on an elastic thing and then twist it and let it go back in. There's an activation energy required. So the molecule goes through a high energy intermediate state, and that's represented here. So this is called an activated complex or a transition state. So here we have that carbon-nitrogen triple bond. It's kind of pulled out away from the rest of the molecule, and it's in the process of turning. That requires energy for that to happen. So we get up here, and then it will go down and finish rearranging over here. So we need energy to weaken that carbon-nitrogen bond, this one right here, carbon-nitrogen, that bond needs to get weakened so that this part can rotate. Activation energy is needed to get there. The higher the activation energy, the slower the rate of the reaction. Okay. Any questions so far? Yes?
Is it also the higher activation energy, the stronger the bonds?
Yes, the activation energy is often related to the strength of the bonds. And so if this bond was stronger, it would require more energy to get to that activated complex. Yeah. And so the activation energy is going to be different for every reaction. So the frequency factor represents approaches to that barrier. So we can think of this molecule here. We've got to kind of pull this out and begin to rotate it. That's like a wagging. So it vibrates from side to side, and how many times does it wag? It's like the tail on a dog. So the frequency factor is how fast that bond wags, goes back and forth. So it's turning out and it's turning back, and it's turning out and it's turning back. And every time it begins to wag out, it has the potential, it's approaching the barrier. If it has enough energy, it'll go over and finish the reaction. If there's not enough energy, it'll wag back. Does that make sense? This is weird. It's weird. You didn't know that molecules could wag their tails, did you? Okay, so that's the frequency factor. That exponential factor, the e to the negative EA over RT part, that's the fraction of molecules that have enough energy to get over the activation barrier. Okay? So it's a fraction of molecules that can do something. So that's going to be a number between 0 and 1. Whoops. Yeah, it's going to be between 0 and 1. If it's 1, it means that every approach is successful. If it's 0, it means that none of the approaches are successful. If it's 0.5, then half of the approaches are successful. Okay? So if our frequency factor was 10 to the 9th per second, and the exponential factor was 10 to the minus 7, then the rate constant, it's equal to A times that exponential component, right? So we've got the frequency factor, 10 to the 9 per second, times the exponential factor, 10 to the minus 7. And so we end up with a rate constant of 10 to the 2 per second. So the rate constant depends on the temperature and that frequency factor and the activation energy. Questions? So the exponential factor, this part right there, that depends on the activation energy and the temperature. So if we have low activation energy and high temperature, that means that this fraction is getting smaller, and e to the dang, that's hard to explain. When this is small and that is large, then the factor approaches 1. When EA is high and temperature is low, it approaches 0. So it's weird because you've got e to the something in there. So let's just, for instance, well, that doesn't work. Let's try e to the minus 100 and e to the minus 0.001. So this is a large number, this is a small number, right? If EA is big and T is small, low temperature, high activation energy, we're going to get a large number here. So what's e to the minus 100? Oh, sorry, 3.7 times 10 to the minus 44. Is that close to 0? Yeah. If we have a low activation energy and a high temperature, then this is going to be a small number, and we've got e to a small number, e to the minus 0.001 is 0.999. Is that close to 1? Yes, it is. So that's what those words there are talking about. So this is essentially 0, and this is going to 1. So the reaction is more successful when that hump is low and there are a higher temperature, right? The approaches are less successful at low temperature when the barrier is large. Any questions? So how does temperature play into this? Remember that temperature is a measure of the average kinetic energy of the particles in a substance. And it's the average because not all of the particles have the same energy. Some are higher energy and some are lower energy. And so we can look at this graph here, the fraction of the molecules as a function of their energy. So here with the blue curve, at some temperature, we see there's a distribution. Some of the molecules have high energy, some of them have low energy, most of them are somewhere here in the middle. This dotted line, dashed line here, represents the activation energy. In order for that approach to be successful, the molecules have to have enough energy to get over it, right? So any molecules that are higher in energy than the activation energy will be successful when they approach. So for the blue, the molecules that can do that would be the area under this blue line. When you increase the temperature, obviously the average kinetic energy goes up, but not only does it go up, the distribution broadens, it spreads out. So the pink line here is at a higher temperature, the average is higher, but this curve is also broader, it's flattening out. So then when we look at the area under here representing the number of molecules that have enough energy, we see that there's a dramatic increase in how many molecules have enough energy to react. Does that make sense? So, summary. Frequency factor is the number of times the reactants approach the barrier per unit time. The exponential factor is the fraction of approaches that are successful. That exponential factor increases with increasing temperature, but it decreases with increasing activation energy. Because if the barrier is high activation energy, fewer molecules are going to be successful. Right? If it's low, more of them can get over. At a higher temperature, the average kinetic energy is higher and the distribution is bigger, and so you have a lot more molecules that have enough energy to get over. So increasing the temperature increases the success rate. Decreasing the activation energy increases the success rate. Yeah. We're going to stop there.